Dude, if you're moving at a constant speed in a straight line, there's no possible way to prove to yourself that you are moving. What? I can just look around me. Well, how do you know that you're not the stationary one and that everything around you is moving? Your senses certainly don't make you feel like you're moving when in uniform straight motion. It's only when you accelerate that you feel and can know for sure that you're moving. I'm listening. This is because the laws of physics behave exactly the same from any perspective or frame of reference that isn't accelerating, speeding up, slowing down, or turning. This is what it means to be inertial, and any experiment you could possibly perform in an inertial frame of reference will play out in the exact same way. For instance, an object will drop straight down, whether it be in a car moving at a constant 50 miles per hour, a plane moving at a constant 500 miles per hour, or if you're just standing still here on Earth. Uniform straight motion and no motion are indistinguishable. There's no way to tell them apart. So observers in each of these inertial frames is valid in saying that they're the stationary one and that everything around them is moving. Now, if they do accelerate in any way which is measurable, then they've entered what's known as a non-inertial frame of reference, and it's now possible for them to tell that they're the one that's moving. Wow, that's pretty crazy, right? This is known as the principle of relativity. The laws of physics are the same in all inertial reference frames. It's been understood since Galileo, and it's the first of two main principles that make up Einstein's special theory of relativity. I don't know, it just seems ridiculous to say that someone moving in a plane is stationary. Well, from your frame of reference here on Earth, that isn't a valid statement, but to an inertial observer on the plane, it is. You see, motion is always relative to a frame of reference. It only seems ridiculous because we're used to measuring motion relative to the surface of the Earth, but remember now, it's just as ridiculous to say that someone standing still on Earth is the stationary one. What? How? Because the Earth itself isn't stationary at all, is it? I mean, relative to its center, you're moving at as much as 1,000 miles per hour with the rotation of the planet. Oh yeah. In addition to nearly 70,000 miles per hour relative to the sun as the planet revolves around it. Not to mention 500,000 miles per hour relative to the center of the galaxy as the entire solar system goes around it. I could go on. Everything in the universe is moving, so there's no absolute rest or absolute motion that we can assign to anything. It's all relative. This is truly mind-blowing. Just wait until we talk about the second
I have a special treat for y'all today. My dear friend and former college roommate is here from the Johnson Space Center in Houston to talk to us about our space program. And yeah, I know what you're thinking. These guys were roomies. How does one go on to be a fancy scientist at NASA and the other's teaching freshman science at a public high school? Yeah, Sheldon.
I was thinking that.
Thank you. All right, let's give a warm welcome to my good buddy, Dr. Ronald Hodges.
Hey, kids. Hey, glad to be here. And, Hubert, the answer to your question is one of those roomies was busy studying while the other was out chasing high school girls.
Yeah. To be clear, they were all over 18.
Well. Now, what I thought would be fun to talk about today is what NASA's planning on doing beyond the space shuttle. Things like the first manned mission to Mars. Yeah.
Did you see the movie Aliens?
I did.
Did you think it was cool?
Sure, I enjoyed it.
Me too.
Football player, right?
Yes, sir.
Now, of course, before we can set out to explore the solar system, we've got a few minor problems to overcome. Not the least of which is every time we launch, it costs the U.S. taxpayers hundreds of millions of dollars.
Oh, no.
Yes.
If you want to save money, why don't you land the booster rockets instead of letting them drop in the ocean?
That's a cute idea, but it's not technically possible.
Why not?
Well, it's hard to explain. The math is pretty complicated.
Perhaps I could help you with it.
I bet you could. I bet you could. I'll tell you what, here is a NASA patch. Why don't you have your mom sew that on your book bag? Now, who here wants to know how astronauts go to the bathroom? Oh, right. See, now, during liftoff, all the astronauts wear diapers.
People often wonder why I chose to pursue a career in theoretical physics. I usually respond by saying I wanted to unravel the inner workings of the universe.
Yeah, perhaps when Captain Kirk said to boldly go, he meant in one of those. Huh?
But the real answer was I wanted to prove this nincompoop wrong.
Right. Beat me up, potty.
I have a special.
Oh, he's always got it. He's always got it.
Quantum mechanics, if the impenetrable barrier is thin enough, then the object has a non-zero probability of ending up on the other side. So what that means is, on a quantum scale, sometimes electrons can just go through stuff.
Space. The tablecloth is space. The sun. What's happening?
What?
What's happening with the sun and space?
Well, the bread is sinking into the tablecloth.
The sun makes a shape around it in space.
Yes. Now, what happens if I do this? It wants to travel in a straight line, but it can't. Why not?
Because the bread's making a shape.
The apple follows the curves made in space.
Yes. Yes, space is shaped. And that is how gravity works. Space tells objects how to move. Objects tell space what shape to be. And there's a way to prove it. When starlight comes near to the sun, what will happen to it?
It'll bend.
Yes.
Okay, Dimitri, I got it set up. Just climb up the rope. Comrade, I do not think that this will work. What do you mean you don't think this is gonna work? The opposing force and displacement of my gravitational pull on this object here will just pull the rest of it through my portal. You expect me to believe you barely understand American slang, but all of a sudden you know physics? It does not take a degree in physics to understand that something held in place by opposing equal gravitational forces will eventually come. God dang it, Dimitri, just watch! Stop! I guess that was kind of stupid, wasn't it? Okay.
Hey there, London Chappie. So you're wondering, how is physics in video games done? You want to know if it's done from scratch for each game, or if there's some sort of third-party software that companies use? Well, nowadays, most big AAA developers use something called middleware. And middleware is essentially software that handles elements of the game that otherwise you would have to spend a lot of time creating, like physics, audio software, animation software. Like, for example, when you load a lot of games, you'll often see things like this. So on the case there, Havok, that is a physics engine. Now, the benefits of this are physics engines and things like this can be incredibly complicated and take a long time to get right. So having one company that's dedicated simply to making a brilliantly efficient and really good physics engine and using that, it saves a load of time and is probably worth the cost just paying it out. But that's the trade-off, is the cost of it, because usually you have to pay some sort of license, and in a lot of cases, they get a royalty from your game, a small percentage of it. Now, physics can be really expensive on the CPU, so if you don't have access to this middleware or can't afford it and you have to do it in, it can be really, really difficult to fit it in small-scale games. And often the way around this is something called baking, which is essentially where you simulate the physics in an animation program or in a 3D modeling program, so you actually get the realistic physics look, but you bake it into an animation so that the engine isn't having to run it at runtime and it doesn't cost as much. Takeaway from this is that physics is ridiculously expensive in video games, and it's why most things in games can't just be knocked about and moved about under physics, because it would just be too expensive to do. And it's really difficult to code an engine to do it well, which is why most people use middleware or third-party software to do it if they can afford it.
using an electrified samurai sword. We don't actually know what's going to happen. Okay, sweet, it didn't catch on fire. Let's keep going. The metal heat attracts the arc because it's connected to ground.
So the Rasen Shuriken's tendency to fly fat and very straight is accurate physically? Yes. Yes, it is. If you examine the Rasen Shuriken physically, what do we have? Well, you have the Rasengan, which we already established was very stable because of its many spinning masses. And then you have a much larger spinning mass on the outside. It's essentially one large spinning angular momentum stabilized by many smaller spinning angular momentums. And we have something in the real world that acts this way. It's a helicopter. You have a very large spinning angular momentum on top and a smaller stabilizing angular momentum on the fin. Not only does this provide stabilization because it's spinning like a gyroscope, but it also creates force in this direction which will stabilize the entire cockpit. And while Rasengan is not pushing against the air in the same way, the Rasengan has many, many more masses of chakra spinning in the middle like gyroscopes, which would make this an incredibly stable construct. So the
The hyperbolic time chamber in Dragon Ball is impossible. When Goku enters the hyperbolic time chamber, he gets 1 year's worth of training in a single day. That's because time passes 365 times faster in the chamber than in the real world. That sounds like it violates the laws of physics. Or does it? Einstein's general relativity says that time passes more slowly where there is a stronger gravity. That's called time dilation. So if Goku were able to create a place with much more gravity and throw his enemies inside while Goku trains in a space with less gravitational field strength, then he could train for a whole year while only a day had passed for his enemy. So do you still think the hyperbolic time chamber in Dragon Ball is impossible?
The key to combat in Dragon Ball, no pun intended, is how well you can use your ki. Ki is the concept of energy, derived from Buddhist and Taoist beliefs that there's energy everywhere, and the user can use that energy for attacking and for defense, as well as other purposes like healing if one should know the techniques. Characters in Dragon Ball elevate their power and speed by raising their ki. During combat, they're also able to suppress their ki, so that way when they strike an opponent, they can just blow up a building behind them or cause some real damage, because Dragon Ball characters get very strong in the latter half of the series. With these tools, a fighter can manipulate the particles around his or her hands and ignite them, and this is how ki blasts like the Kamehameha or the Big Bang or any sort of energy attack is utilized in the series from a scientific perspective. And the more you train, the more energy you have access to and can manipulate, and thus, you win.
Man, I must have gotten like 50 requests to do Special Beam Cannon, otherwise known as Makansa Papadopoulos. Anyway, I don't want to disappoint you, but the Special Beam Cannon is very simple. In fact, it's so simple, it's what we call in physics a simple machine. It's a screw, a corkscrew to be exact. That's actually why I always thought that Piccolo used two fingers. One is to fire this stabilizing beam in the center, and the other is to fire the corkscrew beam. In many depictions of Special Beam Cannon, we see that the outer beam usually has a more violent energy than the inner beam. That's because the purpose of a screw is to take rotational motion and turn it into linear motion. It takes torque and it turns it into linear force. My guess is that there's not a whole lot of force behind the central beam at all. In fact, we can see here when Moro uses it against Piccolo that the central beam kind of slips ahead of the spiral beam. It's a flexible spinning beam with a corkscrew around it, which means it is essentially a plumbing snake, but like a key plumbing snake. And the clog is, you know, your guts. Roto.
Ooh. It is way too early for me to nerd out this hard, but I have to show you what this reminds me of. For anyone new, I'm a huge Marvel nerd, especially as it pertains to real-life science, and this new Quantum Mania logo reminds me of the old bubble chamber images from the early subatomic particle research. Bubble chambers like these were used back from the 50s to the 80s to try and help scientists uncover the fundamental building blocks of our universe. The kind of building blocks we wouldn't be able to see unless we were really, really small. Inside the bubble chamber, charged particles would pass through a transparent, super hot liquid and they would leave behind these little ionized trails. All this action took place in less than 3 milliseconds. Then again, it also bears a strong resemblance to the Eternals symbology, so what do I know?
Oh. You can! Yes, I can. And I am.
Corlos machine just hit 100,000 millisieverts of radiation. That's fully charged, Barry. Whatever you're gonna do, you gotta do it now.
You're out of time, Flash, and slower than ever. It looks like everyone in Central City is running out of time, except me. Houston, this is ISS.
Problem number 1. With a sequence like this is physics. What makes a superhero fight, or really any fight in film, fun to watch is what grounds it, what provides the impact. The moments where we can tell how what's happening on film must feel. On the ground, we recognize the physics of what's happening almost always. In the air, not so much. We lose any understanding of momentum or impact almost immediately. So, as Shazam and Sivana go hurtling through the sky, we don't have any sense of speed, weight, or gravity, and so we don't sense any danger. We're unable to recognize threat. When Sivana throws Shazam a mile away, we know he's going to hit the ground, and yet we're not surprised when he gets up and he's just fine, because, well, we don't really understand the impact of that fall. And this applies to their powers as well. As they hover above the ground, we can visualize their ability to fly. We're seeing it, so as they shoot magic in each other's direction, we know they'll either move out of the way, because nothing's stopping them, or it will hit them and they'll be knocked backward into, well, nothing, or maybe into the ground, which loops us back to the first problem. So how much of a threat is this, or even a punch? Better yet, take a sequence like this from Man of Steel. As Zod and Superman go crashing through buildings, fleeing each other through walls, we begin to realize something. Problem.
This isn't always true, actually. We have the math for things that don't exist, and possibly never will. One of my favorite examples of this is the Tesseract. Mathematically speaking, these are real, but we can't make one because we don't have the math or the technology that would go into physically building it. The Marvel adaptation was actually pretty clever, since a Tesseract, or a hypercube, is the fourth dimensional representation of just a regular cube. And in the movies, this thing could transport you anywhere, acting as a kind of fourth dimensional portal. Pictures of a Tesseract are kind of misleading because they wouldn't look exactly like this. Every quadrilateral or four-sided area is a square. But due to the limitations of our 2 and 3D space, not every part can look like it, like this section here, which is supposed to be a square. In order to be a Tesseract, every point would need to be a 90-degree angle. Picture this person living on a 2D surface, and this is a square in their world. Creating a right angle off of this shape is what gives you a third-dimensional square. I know it's not technically a cube, but this was the closest I could find. And theoretically, these 90-degree turns just keep going up. So try to think of higher dimensions as these increasing 90-degree turns outside of your dimensional space. A kind of Tesseract was built in France in the 1980s called the Grand Arche. It represents a window into a world where people from different cultures and different backgrounds can coexist. Pretty fitting, actually. Although it looks like a Tesseract, it technically isn't, because these parts right here are not perfect squares. So we can have a lot of fancy math and absolutely nothing real to show for it.
These are my most expensive fails. 1. My liquid venom suit, made from 100,000 magnets and ferrofluid, a magnetic fluid that covers the suit. This suit could only be used once and stain my skin for a month.
Was it worth it?
Total damage, $20,000.
Venom.
2. Yondu Arrow. With the drone over the arrow's center of mass, I was able to get it to fly forward when I whistled a high pitch and backwards when I whistled a low pitch. Which looks great and super functional, but I fried the electronics getting this shot. Total damage, $1,200. 3. Iron Man Jetpack. Version 1 was made of these 2 massive carbon fiber fans on my back and 1 on each hand. Unfortunately, this never made it off the ground. It blew the f*** up. Total damage, $40,000. Version 2 worked great though, except it cost another $40,000. fall to see me blow more money.
This is an incredibly soft liquid armor. It instantly becomes unbreakable upon strong impact. In experiments, when a stone is dropped from the same height onto ordinary materials, it bounces back instantly. However, when it falls on the liquid armor, it comes to a stable stop. When you put Armorgul on your hand, you can hammer away without any worries. It can even transform a watermelon's surface into an iron-like exterior. Balloons, which would usually burst at the slightest touch, become invincible with just a small piece of Armorgul attached. This is an incredibly...
I watched the Thor movie, and I'm saying, how much does that hammer weigh? And I heard a sentence in the movie that enabled me to calculate how much his hammer weighed. They say, hammer forged in the heart of a dying star. I filled out the density, and I tweeted it, and I said, if Thor's hammer is made in the way the movie says, it has the weight of a herd of 300 million elephants. That's why nobody could pick it up. The Hulk couldn't pick it up. You need the magical powers of Thor to do it. I watched the Thor movie.
If you're a Marvel fan, you probably recognize Iceman. Over time, Iceman learned to lower his body temperature from a normal 98.6 degrees Fahrenheit to absolute 0 Kelvin. But if you aren't familiar with absolute zero, let me explain. First of all, in order to cool something down, you have to take away its heat. This is done by surrounding a substance with an even cooler substance. But what is heat? Heat is the total kinetic energy of all particles in a substance. So if Iceman removes all the motion from a substance, then its temperature is absolute zero. But here's the problem, Iceman can't create absolute zero. Nothing can. Both classical and quantum mechanics say no to this. Classical mechanics says that you have to have a substance cooler than absolute zero. And in quantum mechanics, nothing is ever stationary through the uncertainty principle. This allots for low energy state motion, which can give you a few microdegrees in Kelvin.
So is Iron Man scientifically possible? Well, first let's dive into his power source, an arc reactor. In physics, it's a theory that's been discussed a lot, and MIT has even been working on building one themselves. The way it works is creating a plasma, a lightning-like substance, from harvesting electrons from normally hydrogen, something that we find in water. In doing so, we must keep the plasma stable with large magnets, which requires the scale of an arc reactor to be massive, unlike the small one we see in Iron Man's suit. However, feasibly and technically, it could work.
When we talk about a hypercube, those are 4 spatial dimensions. Time is not one of those dimensions. But if time is the 4th dimension, can you make a hypercube where time is the 4th dimension? And just to clarify, in the Marvel series, the Tesseract that they describe and they look at and they bring out is a mathematically real object.
Yeah.
Right.
So usually we don't try to compactify time. I'm not saying no one's tried it. On the Earth, I can talk about my local left and right, but there's no global left and right? Like if I go to the right, I'll just come back on the left again. So left is really, really far to my right.
Because 2 wrongs don't make a right, but 3 rights make a left.
So in time, you don't want to be able to come back to where you started.
It's fundamentally a different kind of dimension.
Yes, it is fundamentally a different kind of dimension.
Even though you tell us, and all my relativity professors told me, it's just another dimension.
Still a little different.
So here, Peter Parker Spider-Man needs to stop a runaway elevated train. He shoots out multiple web lines. They stretch a great deal, but they don't break, and he's able to stop the train just in the nick of time. How strong does the webbing have to be for this to work? We can look up the mass of a train. We can estimate its initial velocity by seeing how long it takes to pass city blocks. We can look at the distance over which the webbing stretches. We can estimate its diameter. We can count the number of web lines. And we come up with a tensile strength for the webbing that has to be about 1,000 megapascals, which is equivalent to 145,000 pounds per square inch. But real spider silk has a tensile strength of 1,200 megapascals. If Spider-Man's webbing is anywhere as strong as real spider silk, then this indeed could happen. Around Loki's arm, you see a little blue glow that's coming from the Space Stone that's arresting the momentum of his thrust. It's worth noting that in Captain America: The First Avenger, the Space Stone, which was embedded in the Tesseract at the time, is the only Infinity Stone that was actually weaponized by Hydra and used to create force beams, thereby showing that there is indeed a connection between space and momentum. The first Iron Man movie, 2008, the one that started the whole Marvel universe. I love it. Tony Stark, the superhero as engineer, and the engineer as superhero. When he built his first suit in a cave out of scraps, it was made of iron and was very heavy, at 150 pounds, just counting the iron, not counting the weaponry. Then he developed the Mark II, which was titanium. Titanium is lighter than iron and strong. And then in order to combat the icing problem, he used a gold titanium alloy.
Connect to the Cisco, have it reconfigure the shell metals, use the gold titanium alloy from the Seraphim tactical satellite. That should ensure fuselage integrity while maintaining power to weight ratio. Got it?
Now, there are gold titanium alloys. They tend to be very brittle. They're used in dental applications more than anything else. So unless he's fighting, crime boss Gingivitis, I don't think that he's really would want to use a gold titanium alloy. So much of the technology, except for the arc reactor, are things that we actually have right now. We have exoskeletons, we have plating, we even have jet boots. The one thing we don't have is a power supply. He has an arc reactor that's about the size of a hockey puck and puts out the power of 3 nuclear power plants. If we knew how to do that, we wouldn't need superheroes, because otherwise you'd have an Iron Man suit, but you'd have to drag a long extension cord behind you in order to have enough power for the suit. One thing that's realistic in this is that we never see him, when he engages his boots or shoots a repulsor ray, we never see him press a button or give a voice command. He thinks it, and it happens. That's because he has a cybernetic helmet that picks up his thought waves and sends the information to the suit. This is real. Scientists and engineers at the University of Minnesota and at other universities and institutions around the world are developing cybernetic helmets that pick up the very weak radio waves that are generated when we think, amplifying them, sending them via Bluetooth to another device. They're trying to develop prosthetically around Loki's arm. You see a little...
Why does Ant-Man's suit seem to betray the laws of physics? With the mysterious Pym particles, it can not only shrink a person, but also make them grow. From a real-world perspective, the Ant-Man suit actually violates the law of conservation of mass. When Ant-Man enlarges, his body's density doesn't change. He simply scales up proportionally. This means that when he becomes a giant, he's essentially creating mass out of thin air to fill his body. We can see this in his battle with Vision, where his body remains incredibly solid, capable of flattening someone with a single step. Plus, Ant-Man doesn't just enlarge all his atoms, he replicates them. Given Earth's oxygen levels, when Ant-Man grows, he should be breathing air with 70% oxygen to maintain normal body functions, not the 21% that's typically available. In the ending of Ant-Man and the Wasp, he collapses from exhaustion. But when he shrinks down to subatomic levels, every atom in his body shrinks as well. This is the only way he can reduce his density. If he were to shrink his size without changing his mass, his density would be extremely high. Even climbing onto Iron Man's suit would feel like a needle prick, and he could sink right into Iron Man's skin. From the movie's details, we can see that, as Ant-Man shrinks, his mass decreases accordingly. So his shrinking process also defies the law of conservation of mass. Why does Ant-Man...
At normal size, Ant-Man stands at about 1.7 meters tall, or 5'10". But when he shrinks down to 0.7% his normal size, he stands at about 12.7 millimeters tall, or a half inch. Here's the important part. Despite shrinking to the size of an ant, Ant-Man still has the mass of a 200-pound man. This means Ant-Man is exerting an 890 Newton force over an area less than a square millimeter in size. This equates to a pressure of 890 megapascals or 129,000 psi. That's a lot. To put this into perspective, the compressive strength of your typical stainless steel is about 250 megapascals or 36,000 psi. Ant-Man can't even stand on a table, let alone someone's shoulder. Imagine a pin needle being pressed down with a 200-pound force. He would cut through them like butter.
If you were in Squid Game, you could use science to your advantage, for example in Duck G. During Duck G, a player must flip over a red card that's on the ground by throwing down a blue card. And during the six-legged pentathlon, the players are only given around a minute to do this, so you'd need a strategy. Many people attempted to throw down the blue card perpendicular to the red card because it gives them better grip and precision, but it usually results in the blue card just simply bouncing off the red card and the red card staying where it is. That's because when the blue card hits the red card, only a small amount of surface area is in contact, and therefore only a small amount of momentum can be transferred between the blue and red card. But if you throw down the blue card with its flat side down and aim right for the middle of the red card, you have much better chances. By maximizing the amount of surface area contact between the two cards, you're maximizing the amount of momentum transfer, and this should flip the red card, saving you from a horrible ending. If you were in Squid...
5 times animated shows defied physics. In the Family Guy episode Married with Cancer, Peter attempts to throw a boomerang but ends up throwing himself instead.
See? I told you.
In a SpongeBob episode, SpongeBob manages to light a fire underwater, and Patrick can't help but start questioning it.
If we're underwater, how could there be a...
In the Homer the Heretic episode of The Simpsons, Ned sets up a mattress outside and shoves Homer out the window, but he just bounces right back inside. In the episode Frozen Face-Off, Plankton becomes frustrated that he can't open the secret formula safe and goes to extreme lengths, and ends up ripping an atom in half with his own hands. In the Family Guy episode Absolutely Babulous, Stewie prevents an apple from falling on Isaac Newton, which somehow means gravity was never discovered.
Gravity never happened!
5 times
All Dad needs to do is put his stone inside that circle and they win! Oh my God! Dad threw too hard!
That stone is coming in like a rocket. It's got to be going 4, maybe 5 miles an hour. Someone has to convert that kinetic energy back into potential.
So you've heard about this crazy new Netflix sci-fi series called 3-Body Problem, right? Well, buckle up, because the real-life physics headache it's named after is gonna make your brain do backflips. See, calculating the gravitational tango between 2 objects orbiting each other is easy peasy for scientists. The Earth circling the Sun? They got neat little formulas for that. But here's the mind melter. Add just one more rogue celestial body to the party, and suddenly there's no way to precisely track their combined gravitational dance anymore. It's like the entire system becomes an infinitely chaotic game of interplanetary pinball from that 3-body point on. Each object's gravitational pull constantly scattering the other's trajectories in unforeseen ways. The complexity gets so brain-explodingly bananas that even the fanciest supercomputers can only approximate rough solutions using insane amounts of processing power. So while you're watching those stunning cosmic vistas on Netflix, appreciate just how deliriously unpredictable that gravitational choreography really is behind the scenes.
Squid Game got tug-of-war strategy completely right, and here's why. Firstly, placement. Having the team standing on alternating sides makes a lot of physical sense, creating a puzzle piece effect, allowing stability for the rope. Keeping your feet straight means that more friction is acting in the direction of the rope, and keeping the rope close to your body means the rope is significantly less likely to slip. Leaning backwards is incredibly clever. Putting the force of all of their weight as well as the friction from their feet meant it was much harder for the enemy team to pull them forwards. Finally, pulling, almost like rowing a boat, makes it much more likely for the opposing team to be jerked off their feet, reducing the other team's overall friction, making them easier to pull. That old man really knew his physics, huh? Squid Game got tug-of-war strategy completely right, and here's